going to talk about Node. So briefly, so Node is a server-side JS platform. It's built on Google's V8. It does I/O in a very special way, which I will describe in great detail. It uses the common JS module system, and it's written in C, which has confused a lot of people. So it's a rather large C project, actually. So the thesis is that I/O has to be done differently. We're doing it wrong. Everything, the way that we're thinking about doing I/O really makes things difficult. So writing servers and writing any sort of application is difficult because of how we're doing I/O. So a lot of web applications have such line of code, like you query a database, and then you return a result, and then you use the result. And so the question is, what is your web framework doing while this line of code is running? So in many cases, you're not doing anything at all. You're just sitting there while the database is waiting to respond. And that might be that the database is in San Francisco, or it might be... Thank you. There's a lot of reasons. Okay. Well, the point is that you can't just wait for it to respond. There's a big difference between what happens inside your CPU, inside your memory, and what happens when you go to something outside of that. If you go to a disk, or if you go to a network, if you have to do a TCP connection to a different server, even if it's in your same hosting center, then you're talking about millions of clock cycles instead of hundreds of clock cycles or tens of clock cycles. So you can't do nothing. So obviously better software can do better than just wait for the database to respond. It can multitask. So you can have different threads of execution running. So the question is that the best that we can do? And I think you can look at two popular web servers and see how they're doing I/O and decide if what they're doing right and what they're doing wrong. So here's a benchmark, which is possibly not visible to you, but it shows concurrency, like the number of concurrent clients on the web server on the horizontal axis, and on the vertical axis, it shows requests per second. And so this is Nginx and Apache. And what you see is that the Nginx is responding faster. Not so much faster, twice as fast, 3 times as fast, especially when you get to higher concurrency. Who cares? But the big difference is when you look at versus memory. So again, on the horizontal axis is the number of clients on your server. But now on the vertical axis, you have memory. And it looks great on mine. Okay, so the point is that Apache uses tons of memory. When you start getting a lot of clients, if you have 3,000 people connecting to your Apache server, you're using many megabytes of memory. Whereas Nginx stays very stable. It stays with a small footprint. And the question really is, what's the difference between these two? And the big difference is that Apache uses threads for each connection, and Nginx uses an event loop. Okay. So to be slightly technical, the first benchmark kind of tells you that context switching between the different threads, which is what Apache does, is not free. It costs some CPU time. And the second one is that each thread takes memory, and that ends up being a lot of memory. And kind of in the building tight little server thing community, if you want to make a little Nginx server or you want to make a little IRC server, everybody knows that you can't use threads for connections. This is not the right way to do concurrency. The right way to do concurrency is to have a single thread and have an event loop. So you do something, and then you're done with it. And then you do something else, and you're done with it. What that requires, though, is that what you do never takes very long. You have to have non-blocking I/O. So Apache uses OS threads. There's other threading systems. You could have green threads, or you could have coroutines. These can help the situation very much, but it's still machinery. It's still something that needs to be done. You have to do something to create the illusion that when you connect to the database, your program halts. You don't move on to the next line until it comes back. It's an illusion. Your program's not halting. It's doing all these other things, but it looks like it's halted. So I say that threaded concurrency is a leaky abstraction. It creates pains. You have locking problems. You have these memory problems. It's hard to think about. It's not a very good abstraction for what's really happening on your computer. So code like this, where you call a function and it connects to some server and returns something from that server as if no time has passed, and then you're going to use the result beyond that. This somehow either requires blocking the entire process, or you're going to have some sort of threading system. Maybe it's coroutines, but it's probably going to require multiple execution stacks. But you could have code like this where you make the query to the database, and instead of waiting for the response inside that function, you give it a callback in one form or another. When this happens, your execution can run right through that statement, make that request, and continue doing other things. When the request comes back, millions and millions of clock cycles later, you can execute the callback. There's no machinery involved in this. All you need is a pointer to that callback. So this is how we need to do I/O. If you want very fast, high concurrency servers, you have to design them like this. So, okay, you say, yeah, but everybody's talking about threads. You know, my boss says that Java threads are super cool, blah, blah, blah. Why isn't everybody doing this? Why should you believe me? Well, there's two reasons. I think they can be summed up in two reasons anyway. And it would be cultural and infrastructural. So I think that there's a cultural bias against doing non-blocking I/O. You know, your first program that you ever do I/O with is something where you enter your name, and then you get the result. Somebody types that in, but you block on that function. You don't do anything else. And then you print out the name. So we're taught to, demand input. And we kind of treat it the same way on sockets. So we connect to the database, and All right, give me the response. So people see code like this, where instead of waiting, you just give a callback, and they say, I can't do that. That's spaghetti code. That's too complicated. I think we should reconsider this. I don't think it is necessarily more complicated. Maybe in the simplest cases like this, but when you start writing an IRC server, it becomes very natural to write code like this. And the other reason would be the missing infrastructure. So remember, if you're on an event loop, you can never block on I/O. You can never wait for the database to respond because you're in a single thread. If you ever wait, everything else shuts down. Where in a threaded environment, you can wait occasionally or for very long periods of time. So the problem is that we just don't have like libraries available to us to do this sort of non-blocking I/O. So just a couple of examples, like POSIX has an asynchronous file I/O specification, but it's really hard to find such libraries. Man pages often don't state if a function's going to access the disk or not. You just don't know, which is important. Closures and anonymous functions you don't have in C. So that makes writing such evented code difficult. And things like libmysql client don't support asynchronous queries. I think they actually might do asynchronous queries, but not asynchronous connections. And asynchronous DNS resolution is really difficult to find. So there are certain solutions. You might have heard of Event Machine or Python's Twisted, or if you come from Perl, any event. These are libraries that provide such an event loop with non-blocking sockets. And it is fairly easy to use them to create efficient servers. But I think that users are kind of confused as how to use this. If you're using Ruby, there's all of these libraries available. And you have Event Machine in here, and you want to know, how do I use these other ones? And usually the answer to that is you can't, because the MySQL library for Ruby blocks on everything. So you can't just throw that into an event loop. But people don't know that, and so users really still require some knowledge of event loops or non-blocking I/O, which almost nobody has. And so it doesn't abstract the problem very well. But yeah, luckily JavaScript was designed in such a way that it was built for an event loop. The browser-side JavaScript that you have is an event loop. You create a button. Somebody clicks it, you get an on-click callback. This is exactly what one needs to do event loop stuff. So yeah, it has anonymous functions and closures. When you're on the browser, you only get one callback at a time. You're not getting multiple callbacks, and you don't need to lock variables. And the I/O is just done through those callbacks. So I think everybody in this room who is familiar with JavaScript is already kind of prepared for writing evented servers. You don't really need to know that much more. So, right, so that was a long motivation. So what I want to make is a non-blocking infrastructure so that you can make very highly concurrent servers, and you don't need to know about it. We're going to abstract all of the difficult non-blocking event loop. You don't need to know about that. It's just going to be callbacks. So, right. So let me just give some design goals, and then I'll give some actual practical examples of how to build a server. So first of all, no function should perform I/O to receive disk or network information from another process. You have to have some sort of callback. So you can never have that sort of function that makes some query that returns something. That's not allowed. It should be low level. So I want everything to be able to stream in and out. I should never force the user to buffer data. And if you're familiar with like Ruby on Rails or something, a lot of places force you to buffer data in one way or another. I don't want to make those choices for you. It's low level. People can build on top of that. So if they want to buffer their data, then they can do that. But at my level, at the node level, it should not make any sort of decisions like that. And similarly, I shouldn't remove any functionality at the POSIX layer. So for example, have closed TCP connections. Everybody's shrugging, but there's good stuff to be had that everybody ignores. And so I should also have like some built-in support. You don't want to write everything. I want it to be low level, but I think TCP and DNS and HTTP are infrastructural protocols. They're very important, and so there should be very good support for them in such a system. And in particular with HTTP, it's going to have many features. So we're going to have chunked requests, chunked responses. I'm going to have keep alive, and importantly, you should be able to get a request and respond to it at will. So you should be able to hang requests, and this is what you need for commit-style applications. If you want to do a long poll, then you have to hang that request and wait till you have something to tell the user. And finally, the API needs to be familiar. So if I'm going to have a timer, I'm going to call it set timeout. It should look like browser JavaScript. And where it's not browser JavaScript, where I'm talking about POSIX stuff, then it should use the POSIX names. That is, I don't want to reinvent what people are doing. I just kind of want to present an idealized version of that. And then finally, it should be platform independent. At the moment, I don't compile on Windows, but there's no reason I can't, and I hope to soon. Okay, so now some actual examples. So Node you have to compile it, so you have to download it. So there's no binaries, is what I want to say. And there's no real dependencies other than Python. So it should be fairly easy to build. It's not very difficult, or at least it should not be. Okay, so here's your first example. This program is going to output hello after having waited 2 seconds. So first we require the sys module, which we need to output some data. This is the CommonJS require. It uses the semantics defined by CommonJS. Then we set a timeout for 2,000 milliseconds. Importantly, the callback inside is not done right now. First, we print hello, which comes after that. 2 seconds later, world is printed out. So Node, after the world is printed out, Node exits. So that's kind of important. When there's nothing else to do on the event loop, if there's no more timers, then it exits. It's the end of the process. Okay, so here's what you would do. You would put it into a file called helloworld.js and then run it with the Node program. And you get hello. 2 seconds later, world, and the process exits. Okay. So now we're going to change the hello world program. And what we'll do this time is we're going to go in a loop. So we're going to use the set interval function. And we're going to loop forever and print out a message. And then what we want, when the user kills it, when they hit Control-C, that it prints out a message and then exits. And this is to demonstrate the special process object in Node and how you set a signal handler for the interrupt signal, the SIGINT. Okay, so again, we do the require. We just need one function, so let's just pull it out into a variable. In the next 3 lines, we set up the interval, which calls that callback every 500 milliseconds. Right, and then the last couple lines, we're setting up a signal handler. So you do this by calling this add listener function, which is should be fairly familiar if you're used to the DOM. Then you print out goodbye, and then you exit the process. So this process object emits events when it receives a signal. So it emits the SIGINT event. It would be the same for any other signal that the process might get. So this is like the DOM. You just add a listener to catch what the process is doing. There's a couple of other things on the process, like the PID, the program arguments, the environment, current working directory, memory usage, useful things. So the way that process emits these events is pretty typical for Node. So many objects emit events. It's kind of the fundamental paradigm in Node. So like, for example, a TCP server would emit a connection event every time somebody connects. And like if you have somebody's doing an HTTP upload, it would emit, the request object would emit a body event each time you get a packet of that upload. So somebody's uploading a stream, a movie or so to your server, and you get body, body, body. So yeah, all objects that emit events are instances of the event emitter class. Okay, so here's the first TCP server example. So we're going to make a TCP server. It's going to listen on port 8000. And then when somebody connects, we're going to send the peer a message. We're going to say hello, and then we're going to close the connection. So a very simple TCP server. So we have to require the TCP module. That's what we do in the first line. And then we create a server object, S. And that's a TCP server. And then we add a listener for the connection event. And we get this object C from the connection event. That's our connection. We send it hello, we close. And then finally, we have to start it listening on port 8000. So if we tried that, then we would we would put that code into server.js, and you can telnet to localhost at port 8000, and you get hello, and then the server closes the connection. Okay. So we can simplify this a little bit. So the connection listener does it. You don't need to call this add listener. You can just pass it to the constructor. And so we can simplify this program into just a couple lines by doing this. So file I/O in Node is non-blocking. This is something that's usually very hard to do. In Node, it's quite hard not to do. It's a bit the opposite, which is good. I mean, the way that you should be doing things should be easy, and the way you shouldn't be doing things should be difficult. Okay, so what we're going to do is we're going to look at the last time somebody modified EDC password. So first we require the POSIX module, which has all of our file I/O operations, and we pull out the stat function. And we require our puts function, get that from the sys module. And then we call stat on EDC password, and it returns a promise, which I'll talk more about. And then we add a callback to the promise, which gets called when the stat operation was complete. And then finally, we print out the modified time. So these promise objects are pretty common. All the file operations return a promise. And so a promise is an event emitter which emits a success or an error event. So if you do some file operation, you don't want to block because that's going to be a long time. You can't just shut down your server while you spin the disk. So you send off this request to the disk. Okay, tell me what time that file was modified. I'm going to go do other things. And then eventually it comes back and it says, success. I got the answer for you. Here it is. Or error. So the promise.add callback was just API sugar for promise.add listener for success. Okay, so we're getting progressively more complicated. Now we're going to do an HTTP server. We have to require the HTTP module, and we create a HTTP server object. And the callback for this, which is called on each request, gives you a request object and a response object. So then we send the header, the 200 success code, and content type, text plain. Then we send body hello, send body world, and then we finish the response. This is slightly more complicated than if you were at the Narwhal talk before. Tom promotes the JSGI specification. This is more complicated than that, but it's for a good reason. JSGI requires you to rack 2. It's the same thing. You have a function, and then you return the result. So all the processing happens in a single function, which, as I said at the beginning, is something we want to avoid. If you have to connect to the database, then you don't want to have to respond in one function. Now, I think that there's some ways to do that with JSGI, but I like this. I think it's simple enough. So let's try this out. So we put the code into HTTP Server.js. We run curl on it, and we get hello world. Okay, now slightly more complicated. We're going to do the same thing. We're going to have a HTTP server which outputs hello world, but instead of outputting it all at once, it's going to output hello, and then it's going to output world 2 seconds later. So what we do is we put a set timeout in there. So we wait for 2,000 milliseconds in the request callback. So you might wonder, like, okay, who cares? Why would anybody want to do this? But this is important because while the server doesn't shut down when the set timeout is called, it doesn't say set timeout. It's not a sleep. You're not sleeping for 2 seconds and not doing anything else. You're serving requests. So here's a request, here's a request, here's a request. And then suddenly, okay, that one's done, that one's done, that one's done. This is the exact behavior that you need for Comet-style applications. If you need to do a long pull, you have to be able to hang requests in an efficient way. And this demonstrates how you can do that. This isn't the right way to do a long pull thing, but it demonstrates that you can hang requests. So let's try it out. We put it into a file, HTTP server 2, call it with node, run curl, we get hello. 2 seconds later, we get world, a streaming web server. Okay, we can also call programs with node, one would hope. So we can do that with the sys.exe command. Of course, this also returns a promise because it's something that doesn't happen immediately. It doesn't happen in memory. But if you do ls/, that might have to spin the disk. And so there's some time that happens between the time that that starts and the time that that finishes. So we have to have a callback. So we add a callback to the promise object, which is returned from sys.exe, and then we output the output. Okay, so, but I told you before that I never would force people to buffer data, and that just buffered the data. So there's also a lower level way to call subprocess, to make a child process, where you can stream the data through the standard I/O. So you can stream that if you ls on a huge directory, you don't want to buffer all of that data in memory. You want to stream it to the parent process and parse it and handle it, do whatever with it, but hopefully not buffer it. So this is a simple form of inter-process communication. So this is an example of that, where we're going to launch the cat program, like the Unix cat program, which whatever you send to it, it just sends the same thing back. And so we create the child process in line 3. We add a listener for output. So every time that there's some output, it calls that callback. And then in the last couple lines, we write data to the cat process. And so that's sending that hello world in line 11 and 12 to the standard in of the cat process. And then finally we call close, which closes the standard in of the cat process, and cat terminates when its standard in is complete. Okay, so we can create subprocesses, we can create child processes, and stream data in and out of them. Okay, so now I have a demo for you. I wrote an IRC server in Node, just a hack really, but just to demonstrate what you can do. So maybe this will work, maybe this won't work, but let's try to go to irc.nodejs.org and go onto the Node.js channel. Let's see if I can. Okay, so I have my terminal here. I'm actually logged into the server. So first of all, I'm going to connect to the server. Hopefully it's still running and it hasn't crashed. Okay, so now I'm connected, and I will join the Node.js channel. Okay, so if people did that, you can see people talking. So this IRC server is running on Node. This is an IRC client, of course. What I want to do is actually show. Yes. I also have a REPL library, a read eval print loop, and so since we have an event loop, we can add all sorts of I/O to this. This is one process, but we can add a REPL to it without thinking about it, because what we do is we do all on our event loop, we do all the connections, we send all the messages, we come back, and then we can do the REPL things. If we wanted to add an HTTP server to that would also be possible, all in the same process, just by going around the event loop. And since nothing blocks, we can just add as much I/O as we want to. So I show you the REPL now. Kind of. Okay, so it's running on screen, so I'm just going to open the screen. Oh, wrong There it is. Okay, so this is the IRCD repo thing. And so what I can do is I have total control over the IRC server. So, for example, I can kill some of these users off. Yay. Okay, I have full control. I can also make people like say things. This is of course like just JavaScript. Okay. Anyway, the point is we have a repo to the IRC server, and of course if I just Control C it, then everybody will go away, and they're offline now because the IRC server is gone. And if I turn it back on, then it's just there. Okay, so that's my demo. I'm not a very good presenter. Okay. Yeah, so check out the code if you want. It's just 400 lines or so. I think this demonstrates that Node abstracts the real problem of writing an IRC server away. Because if you look at the code of that, it's just, okay, somebody connects, okay, I have a list of users, okay, I send this user that message. It's really quite easy to follow, in my humble opinion. Whereas if you try to sit down and write an IRC server, say, in Ruby, I think you'll find it very difficult. Okay, I guess you can use Event Machine, and you might find it okay. But I think that this really abstracts the problem of writing a concurrent server. So if you want to throw together, say, a message queue daemon, start up Node, type out 100 lines of JavaScript, and there's your message queue daemon that does whatever specific thing that you need it to do. Okay, so just briefly, I talk about the internal design of Node. So Node is not some big monolithic app. It's a bunch of C libraries that are kind of hacked together in various ways. So the V8 is not a little C library, it's a huge C library. That's by Google, of course. The libev event loop and libeio thread pool are really nice little libraries, and they're both written by Mark Lehman. There's a HTTP parser, which is quite advanced. It could do all sorts of streaming sort of things. That's by me. And a socket library by me, too. And then a UDNS is a DNS resolver, which is important. So the way that I do this is there's a lot of system calls that you might do. If you have to access the file system, those system calls, those POSIX system calls can block. And so what I do is I have a thread pool. underneath everything. And I say, okay, I want to do this system call. I want to read a directory. I pack it up, and then I send it off to the thread pool. It does stuff, and then it comes back. Signal handlers are usually asynchronous from the rest of your execution stack. And this thread pool thing, these things are kind of asynchronous from the main Node.js event loop. And so they have to notify, they have to be marshaled back into the main event loop. You have to say, okay, wait your turn. All right, now we can process the signal handler. You can't just do it immediately. When the result comes from the event loop, you can't just say, stop everything, we're going to do this. You have to say, okay, all right, now we can process you. And I do this by using a pipe from the thread pool in and from signal handlers in, and you can select on that pipe. Another thing that I did is I'm worried about what happens if you pipe a huge file into Node. So say this file is 200 megabytes and has a list of domain names, and you want to look them all up. So each line is a domain name, and you want to do DNS resolution on them. But you can't block the DNS resolution, or else it's going to be really slow. What you want to do is read it in, stream it into your Node process, read the lines, do the DNS lookups, and this should all be on the same event loop. So the problem is that in Unix, or in any POSIX system, the standard id file descriptor is going to refer to a file. And you can't select on files. You can't add them to your event loop. You can't just read from them because that's going to block. So what you do is you create a pumping thread, and you have a pipe. And so you do these blocking reads from the file, pump them into the pipe, which goes into the main application. And in this way, you can stream data into the server in a non-blocking way with just one extra thread. These are the sort of things that you might have to know about if you were going to write this yourself. You don't have to do that. It's down below the API that the users deal with. If you're interested, look in the source directory at the coupling. Okay, so what's next? I have to fix some API issues. There's various things that are very kind of ugly. I want to have more modularity. I want to have break up the libraries into DLLs so that the core node process is very small, and that if you need the HTTP server, you would load a DLL to some shared object to get the HTTP parser, for example. I'm going to include some libraries for like MySQL and Postgres into the core distribution. I need to improve performance. That's always an issue. There's some low-hanging fruit that I know about that we can pick and make it faster. TLS support is on its way, and then finally, I would like to do some sort of web worker-like thing, which would probably just extend the child process object so that you can create processes and kind of do IPC between them in a nice way. So right now the version is 0.1.17. I will release 0.2, which will be kind of the first version that I would hope that other people would use. At the moment, I think it's a bit hacky, and if you're experimental, then please use it. But if not, then wait for 0.2, and I think that will be good because I will freeze the API, or at least some of it, and so you can kind of build on it with some confidence that I won't change it out from underneath. Okay, so yes, any questions? So the question is, if you make changes to the source file, will it load in those changes? No, but Felix and I have been hacking on this a bit this weekend. It's something I'd like to add. Yes? So the question is, what do I do with blocking writes? When you have a socket, there's a write buffer in the kernel, and you can only write so much data to the write buffer before it gets filled up. The kernel can't push out all the data to the network as fast as it wants to. There's some buffer that can possibly fill up. So if you're streaming a file out of the socket to somewhere else, then that can block. In Node, it doesn't block. It buffers the data. It will allocate data internally if you do that. And what you could do is get a callback when when the kernel buffer drains. So what you can do if you want to stream a file to somebody, you start sending it, and then you send it, say, a megabyte, which may fill up the buffer, may not fill up the buffer, and then you wait till it drains, and then you send another megabyte. And so in this way, you can stream data. The write buffer will never fill up. What will happen is I'll allocate memory, so in user space. So writes don't block. Yes? So the question is, what is my stance on CommonJS? So CommonJS, I think, has a lot of good proposals. So the module system I'm using, there's a binary proposal and there's a package proposal, which look very good. At the moment, CommonJS has only ratified, I think, the module proposal and the assert, this testing library proposal. So it doesn't define things like I/O. So I think those discussions will be ongoing. I think there's some people who want it more in a blocking state. I want it more in an evented state, and so we'll fight it out over the next couple months or so. Yes? A little bit. I would like to have more money for it. Writing your own open source project requires a lot of effort, and yeah, it needs funding. Yes?